So here's a few practice questions in quantum physics. So we're starting with an experiment where it's observed that when blue light is shone on a clean metal surface, electrons are emitted, but with red light, there is no electron emission. State the name of the effect observed in this experiment. Right, this is the photoelectric effect. So that's a nice mark to get us started. B, describe Einstein's theory to explain these observations. Right, it's quite a few things we're going to want to explain in here. But of course, we need to explain, well, we've got electron emission happening. And then why is it happening for blue light but not happening for red light? This is the important thing. So we want to start off by saying that there is a one-to-one interaction between photons in the light, between photons and electrons. So why is that important? This is telling us, so therefore, the energy of one photon is transferred to one electron. Yeah, this is that was one of the big breakthroughs, wasn't it, in the photoelectric effect and how it was described, you know, getting this particle nature of light. So the energy of one photon is transferred to one electron. So that's an opening statement that we've got. Let's build up our argument a bit more then. So we can say there is a minimum energy required to release an electron from the metal surface. Required, I'll do some of this in shorthand, to release an electron from the metal surface. So this is good. Then we can say that the energy of a photon is proportional to its frequency. So combining those two things is then saying that there must be, so therefore there is a minimum frequency required to release an electron from the surface of the metal. And we can say that that is the threshold frequency. Then we're at the point where we can connect this to the blue light, red light thing. So we can say blue light, well, in this experiment, we should probably put in. So in this experiment, so let's just sneak that in up here. In this experiment, blue light is greater than the threshold frequency. Threshold frequency. I mean, we could have called this F0, might have made it a bit easier, F0. And the red light is below the threshold frequency. So there we go. We've explained all of that. I mean, you could put other bits in as well. It never does any harm on these photoelectric effect questions to put in the photoelectric equation. Have the HF is equal to phi plus Ke max. So our energy of the photon is equal to the work function plus the maximum kinetic energy of the photoelectrons. You can put that in, talk around that. You know, this is already building towards, that is our minimum energy, which then links into, you've got the energy of the photon, you can talk about the threshold frequency from that. I quite like that chain that I've put there, so I'm going to leave that. I'm quite happy with that one. Part C, the longest wavelength of light incident on the metal surface, which causes electrons to be emitted, 480 nanometers. Right, so we're dealing wavelengths here. Show that the work function of the metal is about 4 × 10 to the minus 19 joules. So if we got the longest wavelength, this means that our Ke max is going to be equal to 0. So we're rewriting this in terms of wavelength rather than frequency. So we're going to have an hc over lambda. If it's our threshold wavelength, that'll be our lambda 0, and that'll just be equal to the work function. So putting in the numbers, we've got the Planck constant 6.63 × 10 to the minus 34, multiplied by speed of light 3 × 10 to the 8, then divide by our, bit of a wonky line, our threshold wavelength, so 480 times 10 to the minus 9. Stick all of that in to the calculator, and we're getting 4.1 times 10 to the minus 19 joules. So that's come out close enough to what they wanted. Calculate the maximum speed of an emitted electron when a photon of energy 5.2 times 10 to the minus 19 joules is incident. Right, so in this case, we're not at the threshold frequency or wavelength here, but they're giving us the photon energy. They're giving us the HF or the HC over lambda, whatever you want to look at. So we've got 5.2 times 10 to the minus 19. Take off the work function. So 5.2 minus 4.1 times 10 to the minus 19. That is equal to our KE max, which is equal to a half mv squared. So we've got a 1.1 times 10 to the minus 19. So our v squared is 2.2 times 10 to the minus 19. Then we need to divide by the mass of an electron. So 9.1 times 10 to the minus 31. Stick that into the calculator, square root it, and that gives 4.9 times 10 to the 5 meters per second. Okay, part D, briefly describe one piece of evidence for believing that electrons sometimes behave like waves. Right, the go-to one on this one is that electrons can be diffracted by, we usually go for the thin piece of graphite on this, so can be diffracted when, okay, well, let's go when rather than by, when passing through a thin sheet of graphite. But then it's worth saying how we then know this. Okay, it's all well and good getting some electrons on a thin sheet of graphite, but how you actually observing anything. So we can say producing a diffraction pattern. So producing diffraction rings might be the best way of putting it. Diffraction rings when projected onto a fluorescent screen. Fluorescent screen. Is that it? Oh no, we've still got a calculation to do. Calculate de Broglie wavelength of electrons moving at 500 kilometers per second. Right, so we're using, I've really run out of space. I'll do blue just so I can see what I'm actually writing on here. Our de Broglie wavelength, that is the Planck constant divided by the momentum of the electron or whatever particle we're looking at. So we've got all of these things. I mean, they've given us this 500 kilometers per second. We know the mass of the electron and we know Planck's constant. So we're just putting that into the calculator. So 6.63 times 10 to the minus 34 divided by 9.1 times 10 to the minus 31. And then divide again by, what's this, 5 times 10 to the 5. So that comes out at 1.457 times 10 to the minus 9. So 1.5 times 10 to the minus 9 meters. Okay, that was a beefy question to kick off with. Let's move on to the next one then. In a demonstration experiment of the photoelectric effect, light of wavelength 440 nanometers incident on a clean metal surface causes electrons to be emitted. No electrons are emitted from the surface when the wavelength is greater than 550 nanometers. Define the term work function. So the key thing on this is we're talking about the minimum energy required to release an electron. Minimum energy required for an electron to be released from the metal surface. So again, a nice starter definition to get us a quick mark. Explain how the work function is related to the threshold frequency. We can do a word equation on this. So the work function is equal to the Planck constant multiplied by the threshold frequency. Yeah, that's easy enough. Calculate the value of the work function for this metal. So, right, okay, we're just doing this then. Our threshold, oh, well, okay, they've done that in terms of threshold frequency. We've got a threshold wavelength. So we're having to do that. This is HC over lambda 0. So we're doing our 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the 8, and then divide by our 550 times 10 to the minus 9, which is giving a 3.6 times 10 to the minus 19 joules. Part B, show that the maximum speed of the emitted electrons in this experiment is about 4.5 times 10 to the 5 meters per second. So we've changed then the energy. This is our work function energy, but now we've got the 440 nanometer one. So the energy of the photon that's coming in, we need to work that out and then take the work function off. Yeah, we go into our HC over lambda minus the work function is equal to KE max. So this is what we're doing. We've got our work function here. Now we're changing, we're doing this calculation again, this one here, but with 440 on the bottom rather than 550. So I've still got that sat in the calculator, so that'd be easy one to do. So that comes out at 4.5 times 10 to the minus 19. Then we take off the 3.6. So we've got 0.9 times 10 to the minus 19 is our KE max, which is a half mv squared using mass of electron 9.1 times 10 to the minus 31. So we just need to plug all that in to the calculator and do our square root, and we get 4.447. what it comes out as. So that's our V, 4.447 times 10 to the 5, which is 4.4 times 10 to the 5 meters per second to two significant figures, which is close enough to 4.5. Calculate the minimum de Broglie wavelength of an emitted electron. Right, we're just plugging all this in. This is our V, and our de Broglie wavelength, so it's the Planck constant divided by the momentum, so m times v. These are all numbers that we know, so we're just sticking this in. So I'll reuse this. It's going to be a quick one on the calculator. 1.6 times 10 to the minus 9 meters. Right, that was a bit of a gimme set of calculations. Part C, the light source for this experiment is a discharge lamp containing excited atoms which emit light at several wavelengths. Figure 8.1 shows the 3 lowest energy levels for one of these atoms. Okay. Electron transitions between these energy levels can produce 3 different wavelengths of radiation. Yeah, 2 to 1, 3 to 1, 3 to 2. Transition between 2 to 1 causes the 440 nanometer photons. Photons at 590 nanometers are also emitted. Which transition causes these photons? Okay, so we know that 590 nanometers, so 590 nanometers is lower energy. That's a bit come out a bit wonky, than 440 nanometers, because it's longer wavelength. So we want to have something which has got less energy. So this is our 440 nanometer transition. So it can't be 3 to 1, because 3 to 1 is going to have more energy. So that is going to have to be our 590 nanometers. So therefore 3 to 2. Hence calculate the wavelength of the photons emitted by the third transition. Okay, so energy of 3 to 1 is going to be the energy of 3 to 2 plus the energy of 2 to 1. Okay, so this is, well, these are all HC. We've got them all in wavelengths, so that's, well, let's write that, put it on a separate line. So HC over lambda for 3 to 1 is HC over lambda for 3 to 2 plus HC over lambda for 2 to 1. So all those HCs are going to cancel. So we're just doing 1 over the wavelengths. So that is giving us that 1 over the wavelength that we want is going to be 1 over, was it 440 plus 1 over 590. So we're just working this out, add those two fractions and then take the reciprocal, which is coming out at 252 nanometers, so 250 nanometers to two significant figures. Oh, that was a nice twist at the end of that question. So yeah, quite happy with that one. Let's do one more. I think I've got one more in this set. Yeah, I'll do this one. Right, this question is about electrons and photons. Both electrons and photons can be considered as particles. State two differences between their properties. Right, so we can say electrons have mass, photons don't. Photons do not have mass. And we can say electrons have charge and photons don't. So make sure on these, when you don't just say electrons have mass and electrons have charge, you have to put in the other bit that the photon does not have mass or charge. So photons do not. If you don't put the actual comparison, they won't give you the mark. Even though it's obvious that you know what you mean, you still have to put both bits in. So electrons have mass, photons do not have mass. You could even be really clear on that. Photons do not have charge. But yeah, they can get quite picky about how you word those things when they're marking them. An electron is accelerated from rest through a PD of 5,000 volts. Show that the energy gained by the electron is 8 times 10 to the minus 16 joules. Right, so a volt is a joule per coulomb. So if we take our volts and we multiply it by coulombs, we get energy. So we're doing 5,000 multiplied by 1.6 times 10 to the minus 19. So that gives us 5 lots of 1.6 is 8. And then we've got 3 to take off of our minus 19. 8 times 10 to the minus 16 joules. Show that the speed of the electron is around about 4 times 10 to the 7. Right, we've done this loads of times. So this is our half mv squared. So we're going to say then v squared, we multiply that by 2. So we get 16 times 10 to the minus 16. Then we divide by the mass of the electron, 9.1 times 10 to the minus 31. So work out that fraction and square root it is giving 4.2 times 10 to the 7 meters per second. Okay, well, I've got a bit of the screen below showing there. Part C, explain what is meant by the de Broglie wavelength of an electron. Right, so that is the wavelength of the wave nature of an electron. So it's the wavelength of the wave nature of an electron. And we can quantify that by saying that it is equal to the Planck constant divided by the momentum of the electron. So calculate the de Broglie wavelength of the electron in B. So we've got our velocity there. So we're going to say that the de Broglie wavelength then is going to be 6.63 times 10 to the minus 34. You certainly get used to the Planck constant when you're in the quantum section, divided by the mass of the electron, 9.1 times 10 to the minus 31, multiplied by its speed, which is 4.2 times 10 to the 7. So that comes out at 1.7 times 10 to the minus 11 meters. Okay, all good. Part D, calculate the wavelength of a photon of energy 8 times 10 to the minus 16 joules. So if we're doing the energy in terms of wavelength, that's our hc over lambda. So that means that our wavelength then is going to be equal to 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the 8. Then divide by this energy, this 8 times 10 to the minus 16. That is giving a wavelength of 2.5. I've got that a bit wonky. got that inside the equal sign there. 2.5 times 10 to the minus 10 meters. So again, you get simple calculations in the quantum section. You know, some of the descriptions can be quite long-winded, but the calculations are relatively straightforward. Photons of energy that are incident on a clean tungsten surface causing electrons to be emitted. State the name of this process, right? That's the photoelectric effect. Calculate the maximum kinetic energy of the emitted electrons. Tungsten as a work function of that. Okay, so that means then, because we've got, well, actually this is going to be dead easy. So we've got photon energy coming in. So Ke max is equal to the photon energy minus the work function. Minus work function. So in this case, we've got 9 times 10 to the minus 19 minus 7.2 times 10 to the minus 19. So 1.8 times 10 to the minus 19 joules. So last part, explain why this answer is a maximum value. So we can say, well, most electrons require energy greater than the work function in order to be released. Yeah, really, we're saying, I suppose another way of putting that, which you might add on this here, is the work function is the minimum energy required to emit an electron. So yeah, we said that in the previous question, didn't we? I was just checking back at the start to see if I defined work function at the beginning of this question. It was the last one. But yeah, this is the key thing with work function. It's why we've got a max on kinetic energy here. The work function's the minimum energy for an electron to be released, which is why we then get a maximum kinetic energy. But usually we're going to need more energy than the work function to get a photoelectron, which means that photoelectron will have less kinetic energy because more work has had to be done in order to free it. There you go, 3 beefy questions for our first set of quantum questions.